Welcome to the Deep Dive. We take your source material, strip away the noise, and deliver the knowledge you need fast. Today, we're embarking on a deep dive into the very foundation of Python, the programming language that seems to be, well, running everything from your Netflix queue to advanced machine learning models.
It really is everywhere.
And to start, I think a simple analogy helps. People think programming is magic, but it's really just a specialized language. It's like a detailed recipe.
Yeah, that's a good way to think about it.
You know, if you're following a recipe for something complex, maybe a Norwegian lesson, it has its own vocabulary, a really precise syntax, 1 cup flour, tea salt, and a sequence of operations.
And repetition, like roll and fry each disk until golden brown.
Exactly.
And that's all a programming language is, a structured set of instructions. Our main source, Introducing Python 2nd edition, it approaches this powerful language not as some complex spell book, but as an incredibly efficient set of rules.
So our mission today is to get into the nuts and bolts of Python's core concepts. We really need to understand why it's the fastest growing major language.
And the answer really boils down to productivity and readability. Python is often incredibly terse,
Terse, meaning you just write fewer lines of code to get the same job done.
Right. And that effectively just accelerates your work. It's the engine driving its popularity in data science and at all the huge tech companies.
And just to be clear for everyone listening, we are focusing on Python 3. That's the current standard.
Yes, absolutely. The older Python 2 is, well, it's essentially retired at this point.
But the philosophy behind it is still there, right?
Right, precisely. The core ethos is still strong. I mean, if you've ever looked it up, you'll find the Zen of Python. These principles like beautiful is better than ugly and readability counts.
I think the one that really defines the whole language for me is there should be one, and preferably only one, obvious way to do it.
Yes.
That just immediately cuts down on the mental gymnastics for a programmer.
It creates enormous clarity. But to see how that's achieved, we have to start with the single biggest conceptual difference between Python and Python.
Yeah.
Well, a lot of other languages. It's how it handles data.
Okay, so where do we start?
In Python, all data, a number, a piece of text, a huge list, it's all wrapped in memory as an object.
An object.
Think of every piece of data as being in its own custom-fitted box, sitting somewhere in the computer's memory. And this box, it always has a defined type. Is it a number, a string, and, of course, its actual value?
Okay, so every bit of data is a self-contained object box, but that immediately brings up the idea of mutability, right?
Exactly.
When I put data in that box, can I change it later, or is it sealed forever?
And that is the key difference. An immutable object is like a sealed, clear plastic box. You can see the value, say the number 5, but you can't change that value once it's created. If you want a 6, you have to build a whole new box.
And integers and strings are the classic examples of that.
They are. And then you have the mutable objects.
The lidded boxes.
The lidded boxes. You can open them up, change the contents, all without replacing the box itself. And the fundamental example here is the Python list.
And you can add things, remove things, change elements inside.
All without creating a brand new object in memory. And this is critical for efficiency, but it can also introduce some really surprising bugs if you're not careful.
Which brings us to what feels like the most foundational concept, the one that really trips people up coming from other languages.
I know what you're going to say.
It's that variables are names, not places.
This is so crucial. A variable isn't a memory slot that holds data. It's just a name. It's a reference tag that points to one of those object boxes.
So when I write x equals 5.
You're creating an object, the box with the immutable value 5 inside, and you're just attaching the name tag x to it.
Okay, hold on. If the variable is just a name, not a place, what happens if I then say y equals x? Because in a lot of other languages, that would copy the value.
But not in Python. Here, you've simply attached a second name tag, y, to the exact same object that x is already pointing to. They're sharing the box.
They're sharing the box. So if I then try to change x, let's say x equals 29.
But because the number 5 is immutable, it's sealed, Python can't modify that original box.
So it has to make a new one.
It makes a new object containing 29, and it just moves the name tag x to point to that new box. The original object, the one with 5 in it, is left completely untouched, still safely referenced by the name y.
That makes perfect sense for sealed, immutable data. The name tags can move around, but the boxes themselves are safe.
Exactly. And this whole referencing model is the heart of Python's efficiency. But, as we'll see later, it has some serious implications when those names start pointing to mutable things, like lists.
Let's move on to the simplest nouns we use to build code. The very basics. Numbers and Booleans.
Booleans are easy, true or false. And when you treat them like numbers, true is 1 and false is 0. That's pretty standard.
Okay.
For integers, though, the big deal in Python is their arbitrary size. Unlike, say, C or Java, you don't have to worry about running out of room and causing an overflow error. Python can handle a Google without breaking a sweat.
That flexibility is a huge win, especially for anyone doing serious computation. Now, we have all the standard math operations, but the source pointed out a few key things to remember for clarity.
Yeah, two things really stand out. First, the two kinds of division. A single slash, shy, always gives you back a decimal, a float. But a double slash, that's integer division. It just chops off the remainder.
And if you want the remainder, that's the modulus operator, the percent sign.
Right. And the second thing, which is maybe more important, don't try to memorize all the precedence rules. Just use parentheses. A lot. Make your intention obvious.
Oh, and for readability, you can use the underscore to separate digits, like 100,000.
A great little feature.
So now we jump from data, the nouns, to action, the verbs. Control flow. This is how we choose what code to run, and it all starts with the if statement.
And this is where Python's design philosophy really shines. I mean, instead of using curly braces or end keywords to group code,
It's all about indentation.
all about consistent indentation. 4 spaces is the convention, from the PP8 style guide. If you miss that indentation after a line ending in a colon, your program just fails. It forces readability.
The actual structure is familiar, though. You have if for the first condition.
If for any other possibilities, and then else for everything else. You use your comparison operators like 4 is equal to and 4 is not equal to.
And you combine those with logical operators, and, or, and not.
Right, and a really powerful feature here is Python's understanding of what are called falsy values. It's not just the Boolean false that it sees as false.
Anything that's kind of empty, right?
Exactly. Anything conceptually empty or 0. So, none, the number 0, an empty string, and crucially for later, an empty lister.
So instead of writing something clunky like if len myless, you can just write if not myless. So that's a great little shortcut.
It is. And, for the more technically curious, Python 3.8 introduced a feature called the walrus operator.
A walrus operator.
It looks like a colon and an equal sign. And it lets you assign a value to a variable at the same time you're testing it. It can make some code incredibly compact and efficient.
Interesting. So we've learned how to choose what code to run, but how do we handle text? Let's move on to strings.
Okay, strings. Strings are just sequences of characters. And just like integers, they are immutable objects.
You can create them with single quotes, double quotes, even triple quotes for multi-line text.
But once it exists, you cannot modify a character in place. If you modify it, what you're actually doing is creating a brand new string object.
But because they're sequences, we can do some really powerful indexing and searching on them. You can get characters starting from 0 or use negative indexing where -1 is the last character.
But the real power comes with slicing, using the start.end.set syntax. Just remember, the start is included, but the end is not.
And the classic party trick, the one that always comes up in interviews, is using a negative step.
Ah, yes. Made of a 1. It instantly reverses the entire string. It's so elegant and surprisingly fast.
Beyond just slicing, there are also some fantastic built-in tools, right?
Oh, yeah. Split is great for breaking a string into a list of words. And its inverse, join, takes a list and smushes it back into a single string.
And for anyone starting Python today, when it comes to putting data into strings, there's really only one way to go.
The F string. Please, just use F strings. They were introduced in Python 3.6. You just put an F before the opening quote.
And then you can embed variables or even little bits of code right inside curly braces in the string itself. It's just the cleanest, most readable way to do it.
Absolutely. So once we have our data structures, we need to process them repeatedly. And this brings us to loops.
Now you have your while loop, which is useful when you don't know when you're going to stop. But the for loop it's just so much more Pythonic.
It really is. You loop over the elements in a sequence rather than fiddling with manual counters, which just cuts down on errors.
For element in sequence, it's just clean and safe.
Exactly. And inside any loop, you have your standard flow controls.
Yeah.
Break gets you out of the loop entirely.
And just skips to the next item in the sequence.
Right. But there is one quirk in Python's loops that, well, it always requires a second look. It's the optional else clause.
Ah, the loop's else. It confuses everyone at first.
It does. The else block that follows a for while loop, it's basically a break checker. It only runs if the loop completed normally.
Meaning it ran through every single element without ever hitting a break statement.
Exactly. So if you're searching a list for something and you find it in breakout early, the else block gets skipped.
Yeah.
It's really useful for knowing if a search failed to find anything.
Okay, let's move to the structures we use to hold collections of data. Let's talk about tuples and lists.
We can start with tuples. They're defined by commas, often with parentheses, and they are our second major type of immutable sequence.
Because you can't change them, they're good for things like settings or anywhere you need a guarantee that the data won't be modified.
They're also fantastic for something called tuple unpacking. For instance, if you want to swap the values of two variables, A and B, you don't need a third temporary variable.
You just write AB equals BA.
And it just works. It's so clean.
And then there are lists, the real workhorse of everyday Python.
Lists, yeah. Defined by square brackets. They are the primary mutable sequence. You can mix types in them and you can change them in place. All the core methods are about modifying the contents.
So you have append to add to the end, insert to add somewhere specific.
And different ways to remove things like pop or the del statement.
When it comes to managing the order of a list, there's a really vital distinction to make, isn't there, between list.sort and sorted list.
This brings the whole mutable concept right into focus. The sort method, it modifies the list in place. The original object is changed instantly and returns nothing.
Whereas the built-in function sorted leaves the original list completely alone.
It does. It returns a brand new sorted list object. So you have to be really intentional about whether you want to preserve that original order or not.
This brings us right back around to our foundational concept, naming and mutability. If I have list A and I just say list B, it's list A, and then I change something in list A, I append a new item, say what happens to list B.
List B sees that change instantly.
Because it's the same list.
It's the exact same list object. That simple equal sign just creates a shared reference. Both names, A and B, are pointing to the same lidded box in memory. You change the contents through one name, the other one sees it. It's the source of so many hard-to-find bugs for new Python users.
So we have to be intentional about copying mutable objects. Our source gave us three basic ways: the list method a.copy, using the type constructor list A, or by taking a full slice A.
And all three of those create a new list object. They break that shared reference. You have to be intentional about making copies with mutable objects. Otherwise, you're just working with the same object under a bunch of different aliases.
That wraps up our dive into Python's data objects, its unique naming convention, and the fundamental control tools. I think you are now equipped with the core concepts of Python basics, and crucially, you understand the most common pitfall when handling these data structures.
I do want to leave you with one final thought, though. Building on that very idea of making an intentional copy.
Okay.
We just talked about those three safe ways to copy a list. A.copy, list A, or slicing with that.
Right, to avoid the shared reference problem.
Exactly.
Yeah.
But these methods all create what's known as a shallow copy. That means they do successfully create a brand new list container for you.
Yeah.
But they only copy the references that are